everyone, and thank you for attending today's webinar. I am Deborah Wellston, today's webinar moderator. Please use the chat feature to submit questions, which we'll address at the end of the presentation. We're recording today's webinar, and you'll receive an email with a link to the video and slides. We are thrilled to have Sammi Sadler and Stephanie Williams here today to present the challenges of plastics testing. Sammi received her mechanical engineering degree from the University of Minnesota Duluth and is an applications engineer at Instron. In this role, Sammi works closely with manufacturers to identify optimal solutions for testing plastics. She is actively involved with ASTM committees and regularly attends polymer conferences. Stephanie is a senior product specialist for Instron's melt flow, rheometers, HGT, VICAT, impact drop towers, and pendulum testing systems. Let's give a big welcome to Sammi Sadler and Stephanie Williams.
Hi, everyone. My name is Sammi Sadler. I'm an applications engineer at Instron with a focus in plastics. And today we're going to be discussing the common challenges we face when testing plastics during static testing. Today's agenda will focus on 3 key challenges associated with plastics testing. If there are some returning guests, this is going to be very similar to what we covered in the previous year. These will include our variability in testing results and what factors may be causing this variability, how to increase the throughput and efficiency in your lab while allowing you to test more specimens with greater repeatability, and then lastly, how to stay compliant with testing standards, including some common misinterpretations, as well as some key changes over the past few years. Let's get into test results and why they may show some inconsistencies. So here's a large list of some of the factors that can influence your results. Today, we're going to be talking specifically about specimen alignment, extensometer type, along with extensometer attachment. The first is specimen alignment. Here you will see a specimen that's pretty well aligned within the grips, and these next 2 specimens will be a little bit more and more misaligned. This may be something that you're currently seeing in your lab and will have an effect on your testing results. We did an internal study where we looked at a series of different materials and intentionally misaligned our specimens within the grips. And here you can see that our data is pretty variable, specifically within our tensile strength along with our break location. When looking at a group of specimens that we made sure to align very well, we can see that the data is a lot more consistent. And it can be difficult to eyeball and perfectly align your specimen just by looking at it within your grips. But the good news is that this can be fixed pretty easily. The easiest way to align the material within the grips is simply to implement a specimen centering device. Here we can see that here on a pneumatic side action grip, along with a hydraulic wedge grip. By attaching these to your grips, you can place the material within your grips at the same location every single time to decrease the variability within your testing data. Another thing that you can do is ensuring that your jaw faces are the same width as your material. So for example, thin film testings, a lot of the time the width of a thin film is 25 millimeters. So it would be beneficial to have a jaw face that is also 25 millimeters wide. That way, when you're placing your material within the grips, you can see if it's overflowing on one side or the other to ensure specimen alignment. Another factor that can lead to variability is extensometer placement on the material. Another study that we conducted here was to compare a purposely misaligned clip-on extensometer to an automatic extensometer. To begin the study, we ran a series of tests on a group of specimens with the clip-on extensometer that was intentionally misplaced on the material. As you can see, there's a lot of inconsistency within this data as well, specifically within our modulus data as shown by the circled area. Comparing this to the automatic contacting extensometer, the gauge length is placed very repeatably on the material each time, given it is an automatic extensometer. There's a lot more consistency, and that can be displayed by the tightly grouped modulus data that is also circled on this graph. So both extensometers that we were just talking about are extremely accurate and meet ISO 9513 class 1 and ASTM E83 class B2, making them both extremely precise extensometers. And I do want to point out here that although we are using a clip-on extensometer, these are by no means bad extensometers. It's simply to show that they are more prone and susceptible to human error. But they are very, very accurate extensometers when used correctly. So the type of extensometer that you use will have an effect on the repeatability of your data. So as just talked about, it's mainly due to human error. So choosing an automatic extensometer will allow for a lot more consistent results. Another factor to consider when testing is to ensure that your toe compensation is removed. Toe compensation is the slack within the material. For flexible materials, this can be physically apparent, like shown in the drawing. It's shown as an arc, whereas rigid materials, the toe compensation will show up as a negative force value reading or compressional load. The reason we want to remove the slack from the material before the test starts is because it'll create a low sloped stress strain curve like the one circled here. A toe region is defined as a region at the beginning of the curve that does not represent a property of the material. It's an artifact caused by the takeup of slack and alignment or seating of the specimen. In order to obtain correct values such as modulus, strain, and offset yield point, this artifact must be compensated to give the correct 0 point on the strain or extension axis. So in short, this will produce incorrect modulus data and strain data. So it's important to remove the slack before starting the test. So after the material is placed into the grips and the grip attaches onto the specimen, there will be some compressional forces that are exerted on the material, and that also must be removed. The process to remove the slack from the material before the test begins is called a preload. This is where the crosshead will move to a certain distance to achieve a force value, such as 2 newtons, to remove the slack from the material so it becomes nice and taut. It's important to note that the distance that was traveled during this process is not the specimen straining. So therefore, we should auto balance the strain values after the preload value is met. It's also extremely important to note that all the loads that we're seeing during this process are real and true, and it's advised to not auto balance our load at this point. And it's recommended that a preload and auto balance of strain is used to remove the toe region, which is required by both ISO and ASTM standards at the beginning of each test. To summarize everything that we just talked about, let's look at the impact of all these factors on a cost versus effectiveness graph. So I do want to note that this is not a linear graph by any means. It's just kind of to show this as a visual. So at the bottom, we have our time. So this is depicted as the lowest cost, but in reality, it really depends on how much you value your time. Simply taking the time to visually align your material within the grips and align your clip-on extensometers on your specimen is extremely important. It takes time, but precision is extremely necessary. And given that you don't physically have to purchase any new equipment, it is deemed as a low cost. The next we have here is our specimen alignment devices. As we talked about earlier, it's extremely important to place your material within the grips at the same location every single time. And this is something that comes at a pretty low cost, but is extremely effective. And although a fully automated testing solution is the most desirable due to its precision and lack of impact of human error, It comes at a pretty good cost. Even at lower cost, there's a couple steps that you can take to improve the repeatability within your testing. So a couple things such as powered grips like pneumatic or hydraulic, and then also adding in automatic extensometers as well. The next thing we will discuss is increasing our laboratory efficiency. To demonstrate this, we did another case study comparing two system setups, going to directly ISO 527-2. The question that we sought to answer during the study was, what are the factors that are taking up the time while performing our tests? Here are the two setups that we used. The first one is a more typical setup and arguably a more manual system. So this included a pair of manual wedge grips, a micrometer and calculator, and then a clip-on extensometer. Comparing this to the more ideal system, which is a little bit more automatic, we have our pneumatic side action grips with our alignment aid, along with an integrated micrometer and an AutoX 750, which is our automatic contacting extensometer. Before getting into this a little bit more, I wanted to talk about the cycle time formula. So given that all of these parameters are affected on the cycle time, the test time itself will not be changing, given that you cannot speed up or slow down a test based off of what the standard is giving you. So this is what we focus on to measure the specimen, to load the specimen within the grips, attach the extensometer, remove the extensometer after the test, and then also remove the specimen once the test is complete. So ISO 527 requires the specimen to be measured at 3 different points along its width and thickness, and then after that, they must be averaged. Using a manual micrometer in the calculator compared to an integrated micrometer, the keystrokes were reduced significantly when the micrometer was integrated directly into the software. So this reduced the keystrokes from 420 all the way down to 70. So just by adding a micrometer integrated into your software will reduce your test time significantly. When looking at the specimen insertion and removal, the manual setup takes a little bit more time, specifically because for wedge grips, you have to crank down on them to tighten the wedge grip onto the material to fasten it in place. So this process takes a little bit of time because if your material is not aligned well within the grips originally, you have to loosen it and then adjust it to make sure that it's set up. So with that, that entire process just takes a little bit more time. But with our pneumatic setup, pneumatic grips are just a tap of the foot switch to close the grip onto the specimen. And then with our specimen stops, as we talked about earlier, they're very effective. So being able to place those on our specimen stops, it's going to align our specimen within the grips very effectively as well. And lastly, our extensometer placement and removal. So similar to our specimen insertion, the clip-on extensometer will take some time to place onto the material and account for any adjustments that need to be made, whereas our automatic contacting extensometer will simply attach onto the specimen as soon as the test begins. So given it is automatic, it basically adds no time to this because it's built into the software. From reviewing our ISO 527-2 time-saving studies, there are a few significant things that can be done to decrease our testing time. So looking at our cost versus effectiveness graph, which is similar to our last section, we can see that adding pneumatic grips can add a lot more efficiency to our test time, specifically with specimen stops as well. And then also investing in an automatic extensometer will result in time savings while also producing a lot more repeatability within the data. And then as seen in the study, reducing our specimen measurement allows for a much faster approach. So by simply integrating our micrometers into our software, we'll reduce our test time significantly. And then lastly, to increase our throughput, it is most ideal to go for a fully automated system. But like we talked about previously, they do come at a cost. So those of you running larger operations, such as testing 80 to 100 specimens a day, a non-robotic automated system is a great solution. And then for those of you running at a 24/7, a fully automated system will greatly benefit the efficiency of your test time. The last section we're going to cover today are testing standards. The most popular testing standards haven't significantly changed where it will impact your current testing, but I do want to go over some noteworthy updates that we've seen in the past couple years. ASTM D882 for thin film testing went under revision back in 2018. This isn't necessarily recent, but it is still important to note the changes that we saw from the 2012 version to the 2018 version. So first thing we're going to talk about is our specimen measurement. The way to measure the films have been updated to measuring, quote, several points along its length, unquote, to now ensuring that you take 3 measurements, one in the middle of the material, and then 2 at either ends of the specimen with within 13 millimeters of each end. Another change is that the update has been now updated to subsection 7.5 that states that the specimen must be within 10% uniformity of the thickness based on the average thickness, whereas originally there was very vague wording around how thick your material must be. And then in subsection 12.2, this was added to the 2018 update that revised using an average width of the specimen as opposed to the minimum to stay consistent with how stress and modulus are calculated. And then lastly, our subsections 12.3 and 12.6 were also revised, the tensile strength and the tensile yield calculation to use the original average cross-sectional area as opposed to the original minimum cross-sectional area to stay consistent with how the modulus calculation is calculated. So how will this impact you? All 5 of these updates will directly impact the testing results and testing methods. Given 3 out of 5 of the updates were revisions to the calculations, the method parameters must be updated to include these changes. So once this has been updated in your method, the testing results will see a slight adjustment, but this will just be a one-time update. So once you update your method, you can use that method for the rest of your tests as well. So you don't need to purchase any new equipment. And then ISO 527-3, which is equivalent to D882, was also updated in 2018. All revisions that were added to the update of ISO 527-3 included dimensional changes in figures 1, 3, and 4. Figure 1 for specimen type 2 has been updated for the initial grip separation from 100 millimeters plus 5 millimeters to now include the plus or minus 5 millimeters. And then figure 3, which is specimen type 1B, has also undergone a tolerance increase, adding the plus or minus 0.5 millimeters to its radius. And then figure 4, specimen type 4, has increased its initial grip separation from 73.4 millimeters to around 98 millimeters. So looking at how this will impact you, these updates will impact the dimensions of your material. If you are testing with any of these specimen types, the die that you use must be updated to meet the 2018 requirements. The method will also require an update for the specimen type 2 and type 4 to include the update of the grip separation. So once these are updated in your methods, just like the previous one, you can use that for the rest of your methods. So the next standard that we're going to talk about is ASTM D638. And to not cause any alarm, there aren't any changes in this standard since 2014, but I did want to talk about it since there are conversations happening about additive manufacturing. So there's been several revisions over the years, and the most recent one is in 2022, but there has been no significant changes with respects to the testing method or the equipment required. And although there's no significant changes that happened within ISO 527-2 or ASTM D638, I do want to discuss the topic of elongation versus nominal strain. So first thing I want to do is define what and where yield is. So the yield point, which is when a material goes from its its elastic region to its plastic region. At this point, it will reach a zero slope. So here we can see that in our ASTM graph for point B and point D, and then in our ISO graph on curve 2 and curve 3. From the beginning of the test until that yield point, an extensometer is required by both of these standards to calculate the material's modulus. So it's important that if you're calculating modulus with your material, you must be using an extensometer. So these extensometers must meet for ISO, the ISO 9513 class 1, and then for ASTM, it must meet the ASTM E83 class B2. If a specimen yields, the nominal strain calculation must be used from then. So that means from the beginning of the test up until yield, you will need your extensometer. And then once that material yields, then that extensometer must be removed and nominal strain will be used from then on. According to ASTM D638, the nominal strain is defined as the change in grip separation relative to the original grip separation. So this is calculated using the crosshead displacement rather than the extensometer. So what does that mean? If you're using a clip-on extensometer, the extensometer must physically be removed from the specimen before you can continue the test. If you're using an automatic extensometer, the software must be set up to either remove the automatic contacting extensometer. And then if you're using a video extensometer, it must automatically change the strain source from the video extensometer to the crosshead. So Instron's Blue Hill Universal software uses an algorithm that'll automatically change the strain source for you. So this is very important to note that if you do not have this set up currently, you must be setting this up within your method. So how does this affect your results? When a material does not yield, the results table will include the displayed results up here. So we have our no yield results with our yield results. When compared directly to a material that does not yield, it will include similar results, but it will require our nominal strain calculations and our nominal strain at yield specifically and nominal strain at break. It's extremely important to display the correct results of your material so you're compliant with the testing standards. So here's a list of the most widely used standards and the most updated revisions. So please ensure you're testing to the most updated version of the standards. And with that, thank you so much for taking the time to attend this webinar and hear my 3 challenges of plastics presentation. I'm going to turn this over to Stephanie now.
So my name is Stephanie Williams. I, as noted, am a product specialist applications engineer working here at Instron with our thermal and impact products. And so today I'd like to talk about some of the challenges we see when testing plastics with pendulums. So just to do a quick agenda. Okay, my screen is not saving, guys. Just changing. So I need to see how we recoup here. Is it? Yeah. Let me try this. Okay, so Sammy, what are you guys seeing?
Right now, we're seeing section 2 impact testing with no agenda right now.
Okay.
So usually if you press the right arrow, it should go to the next slide if you're on your note section.
Okay, there we go.
There we go.
Awesome. Thank you. Thank you. Okay, so a quick overview of what the agenda is going to be. Want to look at impact testing with pendulums. What is it? How do we do it? What are the testing standards, the key standards we focus on? Test results, factors that influence the results and solutions. Look at some troubleshooting, increasing the lab efficiency and throughput. So what are factors that can influence test time to get it so that your lab will become more efficient and increase the throughput? So first, I always like, I'm never sure with these things who is familiar with how any given piece of equipment works or not. So always throw in a slide about what the equipment we're talking with, how it works. So pendulum test, very basic, very simple. Essentially, we have a mass, which is the hammer that's attached to a shaft that then is attached to a set of bearings that a dial indicator or an encoder are on. We have a specimen fixture attached to the base, as you see, and then in the specimen fixture, we have the specimen itself that's attached. Simply put, we raise the mass up to the latch position, which is noted as position 1 in the diagram. When we release that mass, it swings down and through the sample, impacts the sample, and then goes up to another angle lower than the first, of course. So we have 2 energy markers. We have the energy we started with at 1. We have the energy we got to as 2. We simply do the math. It's energy, latched energy minus the second energy, theoretically is energy absorbed by the specimen. We know there's some other parts that come into play here with the pendulum, such as center of percussion, windage. Every day you're supposed to run this pendulum a set number of times defined by the standards to determine what's the windage, what's the friction caused by the hammer and the bearings. If you change from one hammer to another hammer, you are supposed to do the same thing. Get that windage, that friction, and then you subtract that as well to get closer to what the truly absorbed energy value is. So this is how a pendulum works. So next I want to look at what are the most common types of impact tests done with a pendulum. And we see them here. These are Sharpie, IZOD, and tensile impact. These are the most commonly run tests on a pendulum itself. So if we look to the testing standards, start with your Sharpie. So the ASTM D6110 was revised in 2023. Some things to keep in mind is the sample itself is placed horizontal to the impact plane with the notch facing away from the point of impact, and we center on the notch. The overview, there is no dedicated fully instrumented version in ASTM. As I noted, the notch specimen centered on the notch. The test itself, regardless of the amount of impact energy you're using, so whatever the capacity of the hammer is, the testing is always conducted at 3.5 meters a second. What you're reporting are the values, the braking energy and impact resistance. So this is braking energy that's divided by the specimen width. ASTM defines a Sharpie to D6110. The sample will be 127 millimeters long. It will be 12.7 millimeters deep. And then its thickness can vary anywhere from 3 millimeters to 12.7. The standard does state the preferred thickness should be 6.3 millimeters, and that's to prevent any twisting or crushing that can happen with the thinner 3.7 millimeter thick sample. ISO 179, similar to D6110, and that it's Sharpie. However, ISO has two methods. They have -1, which is uninstrumented, and then -2, which is dedicated to a fully instrumented test, meaning we have software, we have data acquisition, we have an instrumented load cell or hammer that are impacting the sample. Same as D6110, the sample is in a horizontal position, notch facing away. We center on the notch. Differences, though, between the two standards become ISO 179 parses much finer what the energy any sample can take away from the hammer is. So they end up having two test velocities. They break it down as if you're using a hammer that's from 0.5 joule to 5 joules, you'll have a lower velocity at 2.9 meters a second. If you're going above 5 joules and up, so say 7.5 up to 50 joules, it will be a higher velocity. It'll be at 3.8 meters a second. Again, the reported values are the break energy and impact resistance. Another difference is in sample size. ISO 179, the sample is, I believe, 80 millimeters long, 10 millimeters deep, and they have a set preferred thickness of 4 millimeters. So to be in full compliance with the ISO standard, your sample is going to be shorter, it's going to be deeper, and it's going to have a defined thickness to it. So now let's look at IZOD. IZOD is actually the most commonly run pendulum test in the US. ASTM and ISO both each have a version of it, D256 for ASTM, ISO 180. Both standards were revised in 2023. It's cantilever test, meaning that we're having the sample is perpendicular to the impact plane. The notch faces the hammer, so it's facing into the impact plane. We center on the notch, the same as we did with the Sharpie test. Both standards use the same geometry to the striking face. Both test at 3.46 or 3.5 meters a second. Differences come in the sample size. ASTM is 60 millimeters long, same depth, 10 or 12, I mean, but then thickness can vary again from 3 to 12. ISO is, I believe, 80 millimeters long, 10 millimeters, and 4 millimeters. So they standardize as well on thickness and length depth. Again, ASTM does make note that the preferred thickness of sample is the 6 millimeter. Again, this is to prevent and alleviate any negative effects from the sample twisting or being crushed or any of those adverse effects to using a thinner sample. So now I want to just do a quick comparison here between the standards I've highlighted with the little blue stars where we see some significant impact that can happen. As we see impact velocity, ASTM has a single velocity, ISO 2 velocities depending on the impact capacity of the hammer. Pendulum range, so hammer range, ASTM actually defines it as being 2, 4, 8, and 16 as being sufficient to test polymers. ASTM breaks it down a little finer. They'll go from 0.5 joule, 1 joule, 2 joules, 5 joules, 11, 22, and up to 50. The striker radius ASTM striker is wider and rounder. So because it's wider, it engages further onto the area behind the notch. So the amount of material being impacted is going to be greater than compared with ISO 179, where it is a much narrower, slimmer profile and has a tighter radius. So we have a smaller engagement area behind the notch. As I noted, the specimen lengths and depths are defined in the standards, as well as the notch. And then the acceptable energy range. So what is the acceptable range that the sample can take away from the hammer? ASTM defines it pretty much as 85%. So anything that is a sample that is fails with an energy absorbed value that's less than 85% of what's available, that hammer is fine. They do make mention you should try to use the lowest capacity hammer that you can to stay in that range. ISO, though, parses it a little finer. They say that the energy absorbed has to be higher than 10% of what's available, but less than 80%. And if you're running fully instrumented, you have to be below 20%. You can't cross 20% of what the maximum capacity is of the load cell. ASTM D256, we look at the same. D256 actually defines 4 different test methods in the standard itself. Method A is the most commonly used. They have C, which is similar to A, but we add in a calculation for how much energy does it take to toss the top half of the sample away. D is used to determine notch sensitivity. Here we change the profile of the notch to see how sensitive to impact resistance could different notches be. In E, we actually take the ISOD sample, rotate it 180 degrees, put the notch facing away, and try to get an understanding for how unnotched samples impact energy there. Again, defined pendulum ranges. We talked about the specimen dimensions. There's variability there, as well as the type of notches that are preferred. And again, what do we take away from the standards to how much energy is allowed to be removed? So why are my test results inconsistent? So some of the key factors that can influence results are here highlighted with the star. We're going to step through these just to kind of look at why are they common issues, why do they influence the result. So the frame design, ASTM in each of its standards, it's usually section 6 with Sharpie and ISO, makes a definition about what the pendulum should look like. It essentially comes down to defining that it should be rigid. It should, have reduced vibrations, minimal vibrations due to the construction. It also defines what the hammers should be. They should be rigid. They, should be robust, as well as the striker faces. So one of the things to consider is the frame itself rigid enough? Is it going to reduce or minimize any vibration that might come into play? Because when the hammer hits the sample, there is going to be some vibration. The sample is going to vibrate. The hammer may bounce on and off. What you want to make sure, though, is that all of that is reduced. You want the frame itself to be rigid. ISO itself actually has an entire standard about the design of a pendulum, and that's ISO 13802. And that standard actually walks you through what does a pendulum for tensile, Sharpie, ISOD impact look like.
Okay, we're just going to do a switch.
Yeah. Thank you so much, Sammy. That was a lot of fun. Okay. I don't have my earphones. Okay, so we get now to what the most critical thing about what affects test results. The notch. You wouldn't think such a little divot removed from a sample could cause such heartache, but it can. purpose of the notch is to be a stress concentrator. So basically, when we impact either above or behind the notch, what we're doing is forcing the sample to fail along that notch. Of them, everything 9 times out of 10, when we're asked, well, why is my data different? Why do I have variability? It comes back down to that little itty bitty V there in the center of the sample. Let's see here. So, we're done. What do you think? There we go. All right. So, things to keep in mind. So, here at the bottom, on the left is a good notch. On the right is a bad notch. The good notch, if you look, you see it's nice and clean on the sides. It's clear down in the apex and the bottom of the radius. The bad notch shows signs of being overheated. The discoloration on the sides of the V. You see that the material actually has melted and collected at the bottom of the notch. So now whereas the standard defines how much material will be left below the notch, since we've melted material, that value is going to change. Things to look at with your notching is what speed are you notching the material at? How much material are you removing at every time you pass either the blade or the saw over it? Are you doing a linear notch, or are you doing a single tooth saw blade? Look at whatever tool you're using to cut your notch. Is it within the tolerance? Because the standards do define what the tolerance will be on that notch. So if you're going to cut a notch to a tolerance, is what you're using still within that tolerance? Whatever you're using is going to wear over time. So that comes to when did you last change the notch? The standards define that you should check the quality of the notch. Well, actually, they say you should change the blade or whatever you're using after every 500 notches. I think if you do 500 notches and you look and you're still getting a really good notch, may not be a reason to change right then, but it just goes to say you want to pay attention to how many notches are cutting, and you want to continue to check what the notch is looking like and not assume it's a good notch. The other thing, how much time passed between the time you cut the notch and you take it over to the pendulum and run it. As we know, you're going to heat the polymer up. If you run right to the pendulum and start testing, well, it could still be warm. That can have an effect versus if you let it sit and cool and toughen back up, if you will. So let's see. What do we do? So we did a little study where we used a single tooth or rotary cutter, and we used a linear cutter to see, well, what do the results look like? How repeatable could each of these be? And as you see with the linear cutter, if the notch radius tolerance was plus 0.25 plus or minus 0.05 millimeters, our linear cutter with the red is right on within that tolerance. However, the rotary cutter varied from being too low or too high. So we got much more consistent notches using a linear cutter than we did using the rotary cutter. Another thing to pay attention with notching, how do you cut it? I mean, there are all sorts of different ways. Milling machines are what they tell you to cut metals with. We use a broaching or a linear knife, where we find that does a much better job than the rotary cutters, as we saw on the other slide, in cutting the notches. Another thing to pay attention to, we find 20% of customers testing with a pendulum condition their samples. So they are looking for that ductile to brittle transition curve And so how you condition and how you handle the sample after it's been conditioned. So what are you doing to move the cold sample into the pendulum can come into play. So as we know, we see, look for where we go from a ductile to a brittle. And ways that you can cool the sample is walk-in freezers on the far left, or a lab freezer. Samples are usually put on a wire rack and then put in the freezer, allowed to cool to the amount of time, and then brought over to the pendulum and loaded and tested. Maybe a better way is a little, I call it a little Pez dispenser box, if you will. This is a small cooling chamber where the samples would be loaded in a holder that put into a freezer, a lab freezer, and then put the holder into the box. The box is mounted either on the table, the laptop, bench top, or on the pendulum itself. And then you just, as you go to test, you would dispense a single sample and put it on the fixture. And then, of course, the top of the line would be a system, a chiller that sits on the pendulum itself. And so it also sits on the fixture. So both the fixture and the samples are all at the same temperature. What this means is that when you're moving, if you have a material that is sensitive to changes in temperature, I've got the fixture at the same temperature as the samples. And so I'm minimizing any negative effects of thermal changes as I put a cold sample onto a warm temperature, onto a warm fixture. So we talk about that as well well, how are you moving? How are you taking them out? How are you positioning them? Are you using a proper tool? Think about it. If you're using a pair of pliers, well, wherever you're grabbing, that surface is going to be heating up. If you're just taking your hand and dropping it in, that again is going to heat up. And 9 times out of 10, usually where you're going to be doing that, it's going to be around the notch. So we're going to be heating up that area that is our stress concentrator that we're getting this impact resistance value from. So rather than using your hands or a pair of pliers, we recommend using a dedicated set of tongs to handle it. So how do we increase your laboratory efficiency? So similar to what Sammi showed, we have a cost effectiveness. What we have is choosing your setup, very basic here, old-fashioned manual dial, maybe a digital readout. You're going to have to do everything manually. If we step up to a system that has a pneumatic release, and maybe an encoder, an onboard system that reads the encoder, we're now letting the system do the work for us. The manual system becomes very labor intensive because of how much you have to do to get the windage factor, correction factor, whereas the system that's a little more automatic, it's done for us. Other things to look at, IZOD vice clamping. Samples are sensitive to clamping. Manually tightening can variability from operators, so we could look to overcome that by having, say, something, a lever action where it's defined, or a pneumatic. We can look at adding software. Standalone versions of software can help us. Things like having software that has defined templates or walkthrough testing processes can help getting all the data in, as well as anything with onboard help, because you're using software, helps the operators report templates where you can get them out and already defined without having to copy anything from an Excel spreadsheet. If we look at these differences, we say everybody's got to handle the specimen. You got to measure it manually, micrometers versus a digital micrometer that might port those directly into the system. The test starts the same, placing the vice. closing safety doors, releasing. If you have a motorized or pneumatic system, the operator's not doing it. You're hitting a start button. And then at the end of the test, I've got to do something with my results. I have to copy them off, put them in an Excel spreadsheet versus using software where it's automatically printed out. So when we look at it, as we measured it, if we do the ideal setup, we can have a 32% faster. So we look at the time, that's going to increase your throughput. So checklist real quick. Are you using the right hammer, pendulum installed properly? Do you have good notch? Are you clamping securely? And then look at the most recent standard. So as you see here, you, as Sammy said, check the standard, make sure you're using the most recent standard so that you're following as it's laid out. Okay. And so if you'd like to contact us, we have more how you can learn about Instron through the QR code, or I believe you have our contact information as well. So thank you for listening.
Thank you. Let's take some questions from the chat window. The first question, does sample location within the grips matter? Sample location meaning front to back in the grips. Does the sample need to be in the center of the grips?
Yes, so it should be in the center of the grips, both front to back and left to right, I would say. The most centered you can have it in the load string is the best, because that's where all of our load is going to be centered in it. So that's going to be the best location, is right in the middle.
Okay, next, how do you determine the preload value?
So the preload value, it is going to be material dependent. To make a material taut within the grip, so nice and straight, it does require most of the time at least 1 Newton of force. So what you want to do is at least have 1 Newton of force as your minimum preload. And then your preload value shouldn't exceed it shouldn't exceed 10% of the maximum load on your material. So it does take some time to play around with it, but ideally it doesn't go much higher than 10 Newtons for plastic specifically. So it does, I think like a good basic rule is to have it under 10% of the maximum force that your material sees.
Okay, next, can pneumatic grips be used with highly glass-loaded samples?
Yep, so they definitely can. So pneumatic side action grips with our Smart Close Air Kit. So this is going to allow you to adjust your air pressure of your grip through the software. So you can change it between 30 and 90 PSI. So depending on how large your grip is, it's going to change the gripping force. So a 10 kilonewton grip is going to offer a lot more gripping force at 90 PSI than a 1 kilonewton grip is. So by lowering that force, making sure that you're still using a decent amount of air pressure within your grips to hold it, and then pull your sample apart. It might take some time, but ideally, you don't want your material breaking as your grips come and close them. So you want to make sure you play around with that too. But yes, you definitely can use pneumatic side action grips for glass specimens.
Next question, can you explain the unit differences between all impact tests, ISO versus ASTM?
So could you repeat the question, Deborah? I didn't get it all.
Yeah, can you explain the unit difference between all impact tests, ISO versus ASTM?
All unit test, ISO to ASTM. I think I'm gonna have to look into that and get back.
Okay. Next question, how are the specimen alignment aids in tensile testing set properly to keep the sample properly vertical?
Yeah, so for our specimen alignment devices, they attach directly to your grip. So depending on what type of grip that you have, it will require a different type of specimen alignment device. So with that, it is kind of like a hockey stick. So it's an L-shaped piece of metal. So that is adjustable with a couple of set screws on the grip itself. So that can be adjusted from left to right and then up and down. So once you have that set, based on your material dimensions, then you can lock it into place and make sure that it's used and your specimens are inputted into the grips at the same location each time, because not all specimen tabs are the same dimensions, so they will have to be changed if you have different dimensions of materials.
Okay, next question. How do I know if I'm using the correct nominal strain calculation in my test?
Yeah, so I would definitely go back to your ISO or ASTM standards. So they're going to have the correct nominal strain calculation within there. By default, always go back to your standard to make sure you're complying with that. But if you have Blue Hill Universal, we have a nominal strain calculation within our test that'll automatically change your strain source from your extensometer to your crosshead. So with that change, as it goes from the beginning of the test to yield and then after yield, if you use that in same calculation, the algorithm in the Blue Hill Universal software will automatically do that for you, and it will comply with method B of ISO 527-2. I can't quote that off the top of my head, but ISO 527-2 is compliant with our Blue Hill Universal software and our algorithm.
Okay, those were our questions. Thank you for an enlightening presentation. Do you have any final comments?
No, thank you so much for listening.
Very good. You will receive an email with a link to the presentation and recording. Please be sure to check out upcoming webinars and have a great day, everyone.